Welcome back to the wonderful world of astronomy. This is Chapter 13, Other Planetary Systems, and this video is part 1 on exoplanets. Exoplanets, otherwise known as extrasolar planets, these are planets that are outside of our solar system. Now, I give these two words when this branch of astronomy was in its infancy. They were called extrasolar planets, meaning outside of the solar system. But in the past decade or more, the term that's been used more favorably has been exoplanets. But you'll see it both ways, exoplanets or extrasolar planets. As of April 2026, this is the record here of exoplanets that we've discovered, 6,273 confirmed exoplanets. And among those, 4,694 planetary systems have been discovered. So some of these planetary systems or other star systems with planets have more than one planet. 1,049 of them have more than one planet. And they've also discovered more than 7,000 potential exoplanets. Now we're going to get into this video how we discover these exoplanets, how we find them, how we confirm that they're actually planets, because it's a difficult thing to do to be able to find planets that are pretty dark. They're not stars, so they don't emit their own light, and they're pretty far away, so it's very difficult, and we'll get into in the video how we do that. Up at the top of the screen, I have showed what was on the previous screen, but just to compare the numbers, so that was as of April 2026. But you go down to the bottom of the screen, because about every semester when I teach this class, I update this slideshow. And this is what the slide said back when I did this in fall of 2022. So you can just compare the numbers here after about 3.5 years, how much the numbers have changed. So back in November 2022, there were 5,246 confirmed exoplanets, which means that in 3.5 years, they have confirmed 1,000 more exoplanets. That gives you a feel for the rate at which this is growing, how many they're discovering. And of those 3,875 planetary systems. So every year they discover more and more, by the hundreds, planets. First they find candidates, things that might be a planet, and then they have to do further testing and confirm that it's actually a planet. And I'll talk about that in this video. The closest star system to us is actually a planetary system. And that's important to note. What we have discovered is that most stars or star systems seem to have planetary systems with them. And there is the Kepler mission, named after Johann Kepler, and it was a telescope that was launched about 2008 or 2009, and its purpose was to discover planets outside of our solar system. And what the Kepler mission found, and subsequent studies have found, is that there are a lot of planetary systems out there. So we don't have to look too far, just to our neighboring star system, and we find some stars. It's a 3-star system, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, and we find that they have planets. This is a layout of those stars. So the two larger stars, Alpha Centauri A and Alpha Centauri B, they're in a tight orbit around each other. And then Proxima Centauri, the one that's actually currently closest to Earth, it's a small red star that has a wider, more eccentric orbit. Astronomers have confirmed 2 planets around Proxima Centauri. And there have been some possible findings of planets around one of these stars. Can't remember which one, Alpha Centauri A or Alpha Centauri B, but those haven't been confirmed. But we definitely know there are 2 planets around Proxima Centauri. So let's look at detecting planets around other stars. How do we find them? And I want to think about the question, why is it so challenging to learn about extrasolar planets? By the way, this picture right here is an image of a star with some planets around it. Now the star is at the center and doesn't look too bright, but that's because in this burgundy color right in the middle, they've just on the picture put a circle kind of to black out, to cover up the brightness of the star, because if we don't cover up the brightness of the star, the light of it will wash out our ability to see the planets. And so with the star covered up, we have planets that have been labeled B, C, D, E, and there's probably an A in there, but maybe it's behind the star, or maybe it's too close or something like that. But at least we see these images of these 4 planets. Now, this is a rare thing here to have an image. What you'll find through this video is that most planets that we find, we don't actually see them. We don't actually have images, but we use other means of detecting them. Let's talk about the brightness and distance of planets. So planets are hard to find beyond our solar system because they are so far away, many, many light years, and they are dim. As I said before, they are not stars. They don't emit their own light. They just reflect a little bit of light that they get from their own stars. To give you a feel for this, a sun-like star is about 1 billion times brighter than the light reflected from its planets. So when you look at a star in the sky, and you can imagine maybe it has planets around it, but whatever brightness you see, the planets around it are going to be 1/1000th of its brightness. So very hard to see in comparison to the brightness of the star. Planets tend to be close to their stars relative to the distance from us to the star. Let me correct that sentence. Planets are close to their stars relative to the distance from us to the star. And just a geometric comparison, this is like being in San Francisco and trying to see a pinhead 15 meters from a grapefruit in Washington, D.C. So imagine if we had a telescope powerful enough to see to the East Coast, and this telescope is powerful enough to see a grapefruit. Could we see a pinhead 15 meters away? That's kind of the geometry of looking at these planets with the stars. Planet detection, 2 main categories of how we detect planets: direct and indirect. So direct means we are actually seeing the light from these planets. It could be pictures like images, or it could simply be spectra of the planets themselves. But more common is indirect methods, measurements of stellar properties revealing the effects of the orbiting planet. So what the planet is doing to the star, that's what we see. And that's what we're going to talk about. All right, so 2 words that mean the same thing: exoplanets and extrasolar planets. Extrasolar planets are what astronomers who have been around for a while, such as myself, might call them, because that's what they were originally called, but now exoplanets is what we tend to call them. They both mean the same thing: planets outside of our solar system. Most of our techniques involve indirect detection of exoplanets. And that could be observing the planet's star's motion. Again, not observing the motion of the planet, but observing how the star moves as that motion is caused by the planet. Observing changes in the star's brightness. Now, how can a star's motion reveal the presence of planets? Well, if you look at this picture, you think about how gravity works. Here we have a star and a planet, and it's not precisely correct to say that the planet is orbiting around the star, but rather it's more precise to say that the 2 of them are orbiting around their common center of mass. Their common center of mass is where the red cross in the middle is. But you notice as the planet goes around, the star itself has a wobble. And the more massive the planet is, the relative to the star, the closer it is, the more gravitational pull it has, the more wobble it's going to have. So we see the wobble of the star without actually seeing the planet. You can imagine an alien civilization peering across space at our sun. They would see, because of the planets, they would see the wobble of our sun. The sun's motion around the solar system's center of mass depends on tugs from all the planets. Now, there's not just Jupiter, the most massive planet. There's also Saturn, there's Neptune, Uranus, Earth, Venus, Mars, Mercury. I just listed them in order of mass. And they all have their different gravitational pull on the sun. And they're all pulling in different directions at different times because they're all moving around the sun at different speeds. And so there's this chaotic wobble to the sun. Now, the sun, you know, is more than 99.9% of the mass of the solar system. So the planets don't have a great effect on the sun, but they have a little effect. If you can imagine this alien civilization with astronomers that are looking at our sun and its wobble, astronomers around other stars that measured this motion could determine the masses and orbits of all the planets. And so this is the wobble that our sun has taken in the past several decades. And they've used a computer to trace it out. Starting in 1960, our sun has this wobble through to 1970, 1975, 1980, 85, 90, 95. Where's it going? 2000, 2005. I've lost. There it is. 2010, 2015, 2020, into 2025 as the sun does this seemingly chaotic wobble. And as I wrote in the second bullet point here, it gets complicated with the 8 planets, but astronomers could actually compute the masses of the planets. And that's what we do. When we look out at stars, we see a little bit of wobble, and we can infer that there's a planet that is going around the star, and we can also calculate based on the wobble, the speed, the size of the wobble, we can calculate the planet's mass and its distance from its star. And what I'm describing here is what we call the astrometric method. So astro just means stars and metric measuring. So we are measuring the movement of a star. We can detect planets by measuring the change in a star's position in the sky. However, these tiny motions are very difficult to measure. They tend to be only about 1,000th of an arcsecond. So of our first method of exoplanet detection in this video, the first has been astrometric method, and there are biases in it. What does it do best? What does it find best? It is best for finding massive planets that are going around nearby stars. Why massive planets? Because massive planets will have more of a gravitational pull on their stars, and around nearby stars, because if something is wobbling, imagine if someone were standing next to you and wobbling back and forth, an inch back and forth, you could see that person wobbling. But if the person were standing 20 meters away, wobbling back and forth an inch, you wouldn't be able to see it as well. You might not see it at all, because the closer something is to you, the more you can see those fine motions. And that's the way it is for these planets. The closer they are to us, the easier it is to detect that wobble. The second method I want to talk to you about is the Doppler method. You learned about Doppler method or Doppler effect back in chapter 5, where when a source of light, it works with sound waves also, a source of waves, I should say, is coming towards you, then those waves get shifted to a higher frequency. Now with light, we call that blue shifting as they go to a higher frequency. But if something's moving away from you, the waves go to a lower frequency, and we call that redshift. And so if you look at this picture, here is a star that's wobbling. Now the point of view, the observers on Earth are down at the bottom of the page. And so the star, as the planet goes around in this big circle or ellipse, and remember we can't see the planet, but we can see the star. And we note that half the time it's coming towards us and its spectral lines are blue shifted. Half the time it's going away from us, its spectral lines are red shifted. So it goes back and forth between blue shifting and red shifting and blue shifting and red shifting. And then that's a way of detecting through the light the wobble of a star. So as I wrote on the screen, measuring a star's Doppler shift can tell us its motion toward and away from us. Current techniques can measure motions as small as 1 meter per second, which is about typical walking speed. This is how the first exoplanet was discovered. It's a planet going around a star in Pegasus. The name of the star is 51 Pegasi. Doppler shifts of the star 51 Pegasi indirectly revealed a planet with a 4-day orbital period. And so here you see a chart as the days go by, and the vertical axis is the velocity. Positive above zero would be going away from us. Negative would be coming towards us. And you can see it's going towards us and then away from us and towards us and away from us. This short period of about 4 days means that the planet has a small orbital distance. Think back to Kepler's third law. With our own solar system, Kepler found that the closer a planet is to the sun, the shorter its orbital period. And you think our closest planet to the sun, Mercury, has a period of 88 days. Well, this planet that they discovered has a period of only 4 days, so it's very close to its star. This was the first extrasolar planet to be discovered around a sun-like star, and back in 1995. And there it is in the sky. There's the constellation Pegasus, there's Cygnus, we have the summer triangle with Vega and Deneb in the constellation Cygnus, and the eagle Aquila, and there it is Pegasus, and there it is 51 Pegasi. The planet around it has a mass similar to Jupiter's. So there's our second method of detecting exoplanets, the Doppler method, and it is best for finding massive planets that are close to their stars. Why is it best for that? Well, a massive planet will have a greater tug on its star, and close to its star, gravity falls off with distance, so the closer it is, the more the gravitational pull. The third method we'll get into now, and I pose the question at the top of the screen, how can changes in a star's brightness reveal the presence of planets? Well, let's look at this. Here we have a star and a planet going around, and through all of this, as I talk about indirect methods, I want you to remember that we can see the star, but we can't see the planet. That's why we use indirect methods. So imagine this planet is going around its star, and there it is at position 1. Now think about what we see. We see a star, and it's got a certain amount of light to it, a certain amount of visible light and the various wavelengths. And then now the planet goes to position 2. And position 3, it moves in front of the star. So it is transiting in front of the star. And because it's blocking some of the star's light, the light that we see dips down just a little bit. It might only go down to maybe 99%, 98%, but it is a dip in the star's brightness. And that's what's shown in this graph to the left. This planet is at position 1, position 2, and then there's a dip in the star's brightness. And then eventually it moves, it's no longer transiting in front of the star, and so we get the full brightness again, and the curve goes up. Now, eventually the planet moves behind the star to position 4, 5, and 6. Now, something interesting there happens as well. Even though when it goes behind the star, it's not blocking the star's light, we do get a little drop in infrared. And the reason is there was a little contribution of infrared light coming from the planet in position 1, in position 2, and position 3. We get a little bit of infrared. Now, we can't distinguish that that's coming from a planet. It's just infrared light that's in with the mix of all the other wavelengths coming from the star. But the neat thing is when it goes into position 5 and position 6, we no longer get the infrared that's coming off that planet. And so you see the chart to the right. During the eclipse, when the planet goes behind the star blocks the planet's infrared contribution. So there's just a little bit of a dip, not too much because the planet is small and it doesn't have that much infrared, but there is a little bit of a dip. So what we see is that as the planet goes around the star many times, there's a dip in the brightness in visible light, and then there's a dip in the infrared, and then there's a dip in the visible, and then a dip in the infrared. And it's a periodic thing. And once it's happened 2 or 3 times, that gives us strong credibility that it's actually a planet going around that star. So let's go over some vocabulary. A transit is when a planet crosses in front of a star, resulting in a dip in brightness. An eclipse is also sometimes seen. That's when the planet passes behind the star. Now, when there is no orbital tilt, meaning if you look at the picture, we're looking kind of edge on more or less of the plane of the orbit. If it were tilted more, I know in the picture it's tilted a little bit so you can see the foreground and the background. The more it's tilted, the less accurate a measurement of the mass we can get. But if there's no orbital tilt, we can get a good accurate measurement of the planet's mass. The Kepler project that I mentioned before, NASA's Kepler mission was launched in 2008 to begin looking for transiting planets. The Kepler mission, it did a continuous survey of over 500,000 stars, watching for is there any dip in brightness between visible light and infrared. It was specifically designed to measure basically a planet that did similar to what the Earth does with the sun. It was designed to measure the 0.008% decline in brightness when an Earth mass planet transits in front of a sun-like star. And it's found over 14,000 planet candidates. So here are our 3 methods of indirect exoplanet detection: astrometric, Doppler, and transit. Now, the transit method at the bottom is best for finding large planets. Now, that can be different from massive planets. Typically, if it's large, it's also going to be massive, but there's not a perfect correlation there. But talking about large planets means it actually takes up, it blocks out more of its star's light. And being close to its star, and that's due to what makes it better, what makes this method better for finding stars or planets that are close to their own star? Well, it makes for a shorter orbital period. So why does that matter? Well, if a planet is moving in front of its star every 2 or 3 days, it's going to be very easy to pick up on that pattern. It goes dim, it goes bright, it goes dim, it goes bright. And every few days it happens. Now imagine if the planet were something like Neptune. Neptune is a very large star, a very large planet, but it takes 160 some years to go around the sun. And so if an alien civilization were looking at our sun and you think about detecting Neptune by the transit method, that would be difficult because the getting bright and getting dim of the sunlight would happen every 164 years. It would be harder to pick up on that pattern. Now, as we look at these 3 methods, I want you to see some commonality, and I want you to see that there are strong biases towards the types of planets that we discover. Massive planets, large planets, planets that are close to their stars. That's the common theme between all of these. And so we tend to find planets that are very big and very hot because they are close to their stars. Now, there are certainly small planets out there and planets far away from their stars, but those are just harder to find. So occasionally you might see in the news, and a lot of the news is clickbait, meaning there's something in the title that wants to draw on your attention, and they'll say, it's an amazing discovery, an Earth-like planet. And I don't want you to be swayed into thinking that they found, like on Star Trek, every planet they land on, or on Star Wars, every planet they land on has air to breathe and the right gravity and all that stuff. That's not what they mean by Earth-like. Typically, what they're talking about is a relatively small planet. And the amazingness of that discovery isn't that we found something that is like Earth, as if we could live on it. but rather it speaks to the breakthroughs that astronomers have made in being able to detect small planets. So the awesome thing about it is that astronomers have detected a small planet. But that sounds boring to, in journalism, astronomers have detected a small planet, so they'll say Earth-like. Now, those three methods have been methods of indirect imaging, the transit method, the Doppler method, the astrometric method. There is also direct imaging. So such as this picture here. This picture is of a star, that's the blue thing in the middle, and the red is a planet. So lately, in the past few years, we have been able to get some pictures of planets. But that's not usually, maybe not at all, how we find planets, because it's very difficult. Usually we find them by one of those other methods, and then we try to put a telescope on it to see if we can get an image. Here's an image I showed at the beginning of this video, 4 planets around a star that is known as HR 8799. And we can tell things based on the spectrum of the star, what type of star it is. We can come up with calculations based on the orbits of those planets, the masses of those planets. And here is a video of it. The planets moving around the sun, or the star. You can see the scale down here, 20 astronomical units. That's about the radius of the orbit of this planet that's closest in there. So if you think back to when you learned about our own solar system, that's about the distance that Uranus is from our sun. Just like in the previous image I showed you, they've blackened out where the star is. Little bit about that star. This will certainly not be on the test, but it's 129 light years away. They know it's a type F05 star. And just as a review, you have a final exam coming up. Think about what that means. I want you to remember the spectral types O, B, A, F, G, K, M. So F is going to be a star that's a little hotter than our sun, being a G star, so it's an F star, whitish yellow. The Roman numeral 5 means it's a main sequence star, as most stars tend to be. They know that because it's an F05, it's 1.5 solar masses, it's 4.9 solar luminosities, and just thinking towards you have a final exam coming up, that makes sense. If it's an F star, it's a little higher up than the sun on the Hertzsprung-Russell diagram, so a little more massive, a little more luminous than the sun. Now, from the orbits of the planets, they can detect that the masses of the planets range from about 5 to 10 Jupiter masses. So pretty big planets. But again, that's the bias of these methods is finding big, massive planets. So in this video, what have we learned? Why is it so challenging to learn about extrasolar planets? Direct starlight is billions of times brighter than the starlight reflected from the planets. How can a star's motion reveal the presence of planets? A star's periodic motion, detected through Doppler shifts or by measuring its motion across the sky, that's called the astrometric method, tells us about its planets. And transiting planets periodically reduce a star's brightness. How can changes in a star's brightness reveal the presence of planets? Transiting planets periodically reduce a star's brightness, and the Kepler mission has found thousands of candidates using the transit method. How will future observations improve our understanding? Transit missions will be capable of finding Earth-like planets that cross in front of their stars. Astrometric missions will be capable of measuring the wobble of a star caused by an orbiting Earth-like planet. And missions for direct detection of an Earth-like planet will need to use special techniques like interferometry for blocking starlight. And that is the end of Chapter 13, Part 1 on exoplanets. Have a great day.